In this video, we're going to explore a common pulmonary test known as spirometry. We'll start off by giving you a bit of an introduction on how the test is carried out, and then take you through an analysis of sample test results. Finally, we will finish off with a practical example to apply what we covered. The aim of the spirometry test is to determine how well your lungs are working by measuring the volume and speed of air moving in and out of your lungs. This information can be used to analyse breathing patterns and diagnose conditions such as asthma, bronchitis, and pulmonary fibrosis. In a spirometry test, a patient starts off by breathing in and out normally. The patient then inhales as much as possible to fill the lungs completely before breathing out as hard and fast as they can to remove all air from the lungs. The volume of air is measured through a spirometer and represented in a graph. A nose clip is used to prevent air escaping out from the nostrils. There are several factors that need to be considered to obtain accurate results. The first is the patient's height, as height is directly proportional to lung volume. The second is age, as the older we get, the less effective our lungs become. The last is gender, as males and females may have different lung sizes. A spirometry test produces a typical graph that looks like the one shown below. This is a sample test result from a healthy adult. The first pattern of waves represents normal breathing. Up represents inhalation and down represents exhalation. The difference in their amplitudes is known as tidal volume. In other words, it is the amount of air we can breathe in and out at rest. For a healthy adult, tidal volume is usually around 500 ml. Another important term is minute ventilation. It is how much air breathed per minute and is calculated by tidal volume times the breathing rate. For example, a healthy person takes in 500 ml per breath and has 11 breaths per minute. The minute ventilation is therefore 500 times 11, which equals 5,500 ml per minute. However, not all of the air participates in gas exchange. This is due to the presence of dead space. Dead space are regions of the respiratory tract that do not participate in gas exchange. For example, our conducting airways, such as the mouth, pharynx, larynx, etc., have a volume of about 150 ml, which does not participate in gas exchange. As a result of the 500 ml of air entering the respiratory system in each respiratory cycle, 150 ml never reaches the alveoli, but is merely moved in and out of the airways. This is known as anatomical dead space. In addition, some alveoli are poorly vascularized for various reasons. Hence, not all of the air that reaches the alveoli participate in gas exchange. This volume of air is known as alveolar dead space. The sum of anatomical and alveolar dead space is physiological dead space or waste ventilation. Due to the presence of dead space, clinicians actually focus more on alveolar ventilation than total minute ventilation to evaluate the effectiveness of gas exchange. I will give you an example to demonstrate that point. Let's refer to the table below. As you can see, Subject A carries out a short and fast burst of breath, while Subject B has a normal breathing pattern. Although A and B have the same minute ventilation, their alveolar ventilation is largely different. This is because there is always a fixed volume of each tidal volume that goes into the dead space. Therefore, any decrease in tidal volume goes directly towards decreasing alveolar ventilation. This also applies for increasing the tidal volume. Returning to the graph, the amount of air that is possible to be inhaled and exhaled is called the vital capacity. From this, we can calculate other significant volumes, such as inspiratory reserve volume is the maximal amount of air that can be increased above the tidal volume in the deepest inhalation. Expiratory reserve volume is the same during the deepest exhalation. This is achieved through maximal active contraction of expiratory muscles. After an expiration at resting state, the lungs still contain a huge amount of air. This is the resting position of the lungs and chest wall in which there is no contraction of the respiratory muscles. This is known as functional residual capacity. Even after a maximal active expiration, there is approximately 1,000 ml of residual volume still remaining in the lungs. The lungs are never completely emptied of air. By adding relevant volumes together, we can get the total lung capacity. However, a spirometry test cannot measure the residual volume, functional residual capacity, and total lung capacity. To get these parameters, we use a technique known as the helium dilution technique, in which a patient breathes in a mixture of air containing a known amount of helium. The patient starts at the lung's functional residual capacity position. After each breath, helium moves into the lung until the concentration remains constant. The diagram below illustrates the changes happening inside the lungs. Stage 1. The FRC, functional residual capacity, is filled with air remaining after the previous expiration. Stage 2. The patient breathes in the helium and air mixture. Since helium is not absorbed by the alveolar membrane, the FRC are gradually filled up with helium while the previous amount of air in the FRC is gradually absorbed by the body. Stage 3. The FRC is completely filled up by helium. At this stage, the helium concentration remains constant unless the patient expires heavily. Because helium is not absorbed, we have a closed system and can apply the formula C1V1 equals C2V2, where C represents concentration and V represents volume. V2 also equals V1 plus the functional residual capacity. Rearranging the original dilution equation, we obtain a result for FRC, where FRC is a function of V1, C1 and C2. The advantage of this technique is that it is relatively inexpensive and easy to perform. We will now take you through a practical example to illustrate the theory we cover in this video. We had a person breathe through a plastic tube with a volume of 500 ml, and this is the data collected. As we can see, the total volume was increased to compensate for the addition to the person's anatomical dead space. The subject took in a larger amount of air. However, the alveolar ventilation in fact decreased due to the increase in anatomical dead space. As a result, there was a build-up in arterial carbon dioxide. In response, the body increases the respiratory rate to return the CO2 levels back to normal.